The first lecture by Johannes Henn on Feynman loop integrals and special functions and differential equations. Yeah, Johannes, please.
Thank you, Jaroslav. It's a great pleasure to be here. I think it's the first time I give a lecture in a long time, so that's exciting. I'm just trying the microphone. Can people hear me in the back? Yeah, some nodding. And then next, you see I wrote the title. I'll do my best. My handwriting is what it is, but if there's any issues, just give me a sign in the back, and I'll try to I'll do my best to improve it. Also, as you can see, I'll be giving a Blackboard talk, so also feel free to come closer. It's the intention also is that I'd really like to develop some material, so I'm afraid some of it might be basic for people who've been working in that area. But so then my message is, so for those of you who haven't seen this before, really do try to follow if you like, and feel free to interrupt me and ask questions. And for those of you who are already more expert in some of the things, also don't hesitate to ask some more advanced questions, because then maybe in this way I can also, say something more interesting for you. Now, there'll be 3 lectures, one this morning, one this afternoon, and then a final lecture tomorrow. It's a bit risky to announce what the plan is for lectures, because experience shows that then it's especially with Blackboard lectures, sometimes the timing is a bit different compared to what one thinks it is. But essentially, my lectures connect to various previous lectures. So in the part for special functions, I think they'll connect to some things you've heard from Lance. So symbols, special functions, iterated integrals. There'll be some connection to that. But then there's also a connection to all these wonderful structures we've heard about for tree level. So in particular, generalized unitarity. This basically has to do with the fact that when we think about loop integrals in quantum field theory, we can view the problem as some loop integrand, so what Jake was talking about, some rational function essentially, that although it's a rational function, has very interesting properties. And so you've learned already a lot about those rational functions, how to think about them. And but then the task is to think about what happens upon the d-dimensional, 4-dimensional, in general d-dimensional loop integration, how those beautiful rational functions get converted into special functions, polylogarithms, and generalizations thereof. And it's very interesting that somehow the properties of the functions, they of course originate from the integrand, and so we'll be able to profit from that connection as well. So that's why there's these 2 things. But then we do get some interesting functions, and so I'd like to tell you a little bit more about their properties and how we can best think about them. And so I've decided now for the lectures to start with some of these functions. So the first lecture I'll talk about special functions that we can see in Feynman integrals, and we'll discuss good ways of thinking about them in, if you wish, a bit of an abstract way, even in the beginning, without needing to refer to any Feynman diagrams or Feynman integrals. But then we'll see how that's connected to Feynman integrals, and in particular how these functions appear in a natural way from the differential equation method. And then, so that will can go into in the second lecture, where we kind of learn somehow the details of the method, how to actually make it work. And then you will discover that in order to fully exploit the method, we can use hints from the integrands that simplify our life considerably. And that, roughly speaking, I'll talk about in the third lecture. So that's the overall plan. Of course, in 3 times 1 hour lectures, they have to select some material. So some things I won't be covering are some of the kind of more standard things that you see in quantum field theory, or maybe a first advanced quantum field theory lecture. So for example, how to go about to do a Wick rotation, or how to introduce Feynman parameters. So maybe some of you haven't seen that yet, and for that purpose, I'd just like to give two references, one which covers really that and a lot of other topics, and then one other reference which also covers many things that we'll see throughout the lectures. So for general reference, I recommend for further reading, there's various great books by Smirnov. I say several, and that's I don't give a specific title. So they've appeared with the editorial Springer. I think one of them is called Analytic Tools for Feynman Integrals, or some version of that title. So that's really very, very extensive. There you can find a lot of useful information. And then I would like to mention some lecture notes that I put on the archive. It's already a few years old, but I think they're still quite useful for this material. So here's the archive number. So that also covers some of the, but in a more streamlined way, a few introductory things, and then focuses on the differential equation method. Okay, so what's the problem we want to study? So Feynman integrals, they appear in many places in quantum field theory. I should say in perturbative quantum field theory. So if you wish, that's one restriction that we're making. But having said that, then they appear really in many places, and roughly speaking, in most situations where you would like to extract some useful predictions out of perturbative quantum field theory, at some moment you'll encounter these loop integrals. So that means that if you'd like to get some answers, it's useful to know how to evaluate them, or at least have a little bit of an understanding of how they work. And so examples are, let's say you like to study correlation functions in position space. So at loop level, you have certain integrals which depend on the positions of your operators. Or staying in that picture, maybe you consider composite local operators. They have some anomalous dimensions. You'd like to compute what those anomalous dimensions are, how they depend on the coupling constant. So that's also a typical problem. Now connecting more to the theme of this school, let's go to momentum space. With Fourier transform, we go on shell, we define scattering amplitudes. There you have a different type of on-shell Feynman on-shell processes and associated Feynman integrals. These are some typical examples, and there I'm thinking about standard flat space QFT, but there's also other applications. So let's say you're interested in ADS CFT and you would like to compute some Witten diagrams. Or yet another more recent example in cosmology, people are interested in cosmological correlators. There, the types of integrals you need are a bit different, but still I'd expect similar methods to be applicable. So what I'm trying to say is, I mean, some of the ideas presented here, they could apply to different scenarios, depending what you're interested in. Let me just formulate I said it earlier in words, but the general problem is that we have some function, I call it I, that will be our Feynman integral, and it will depend on some parameters. I'll specify them in a minute, but the essential. So, let me take, to be concrete. Let's imagine some scattering process. So we have some particles coming in, some particles coming out, like this. So let's say this object, it will depend on the momentum of the scattered particles. We don't really want to place any restrictions on the type of model, type of theory. So there could also be mass parameters, say some internal masses, external masses. And in general, we'll be interested in computing such an object in d dimensions. So d, let's say if we are in, we think we live in 4 dimensions, then in principle we'd like this to be 4. But as you know, in many cases, it's useful to have a dimensional regulator. And so then epsilon will be our dimensional regulator. So in principle, the method I'm describing, it can apply to these cases. Of course, the more parameters, the more deformations you keep, the more complicated the answer is going to get. So that's then up to us to choose and depends on the problem. And then what we have is we have some loop integrations. Let me call the loop momenta K. Let's say we have L loops and we want to have some L loop integral in d dimensions. And then, and I see already a notational problem. Sorry, let me call this F and let me call the integrand I. So then we have some integrand. This is what Jake and others were talking about. It depends on the external momenta. It depends on the loop momenta and all the other parameters as well. So, for example, the masses. And as I said, this is now a rational function. This is a rational function, and the question is what transcendental, what special functions do we need to describe F? So what special functions are needed to describe F? So now you've seen in previous lectures already some of the functions that appear there, and I'd like to actually take this approach that you might have some Feynman integrals that you're interested in, and perhaps you've started computing one of the easier integrals, and you start discovering some functions, and then you wonder, okay, is there some systematics? So I'd like to take this approach to say we already know from some calculations that certain special functions appear. So let's look at them in a little bit more detail, and then from there on let's generalize. So it turns out we actually have an answer to this question, if you wish, from experience, but it can also be proven that in the case where we're at one loop, so L is equal to 1, and we're interested in four-dimensional answers, then we know a certain set of functions is actually sufficient. So we know that for L equals 1 and D equals 4, there's actually two types of functions which are sufficient, which is the logarithm and the dilogarithm. If you haven't seen that one before, I'll define it in a minute. Dilogarithm are sufficient. So that statement is in the sense that we have integrals at one loop which are potentially divergent. That's why we keep the regulator, and we may expand for small epsilon. Then we get some in general some Laurent expansion. So to remember that I should use this. So what do I mean by this dimensional regularization? I mean that if we have this F, which depends on D equals 4 minus 2 epsilon, what we want in general, we want some expansion, K bigger than K0, epsilon to the K, and then we have some expansion coefficients Fk, which so all of these of course depend on the kinematics, and then typically we truncate the expansion at some order. So let's call it some K max that we're interested in. And so if we're interested in one loop processes, then we might want to stop here at the finite part and throw away all the order epsilon terms. And so my statement that logarithms and dilogarithms are sufficient at one loop refers to those functions that we can get up to here. So for typical one loop amplitude, you'd have that K0 is actually minus 2. So it'd be a double pole, then it'd be a single pole, a finite term. And if we're happy with a one loop calculation, we might throw away the higher order terms in epsilon. Okay, so in that sense, it's really useful to know about those functions. Of course, in the lecture, I'll not be restricting myself to one loop, so then later we'll also want to consider more general functions. You've heard from Lance, I think, about functions which appear up to 8 loops and higher. And then so these are called multiple polylogarithms, and then there's also functions beyond that, and also mention, I won't focus on those in this talk, but I'll also mention a few useful things about them. So okay, so so far so good. So what are logarithms and dilogarithms? I suppose everyone knows the logarithm, but just in case, we can write it as a one-fold integral like so. And maybe it's just worthwhile pointing out what are its analytic properties. So the logarithm is a multi-valued function. You see the integrand has a pole at 0. And actually, there's a branch cut, and it's up to us to define that. I think you know this, but if this is the complex x-plane, then a typical choice is to place the cut here on the negative real axis, and then this integral means that we start integrating at 1, and then depending on where x is, if x is on the real axis, we just integrate there. If x is complex, then we could integrate in some way to where the function argument is. Okay, so that's the logarithm. We'll be looking at differential equations. So it's also important to record what is the derivative. Well, it's just trivial. So that's 1 over x. And now it turns out that the dilogarithm can be defined in a similar way, but just as opposed to having one integral, we'll be having 2 integrations. So we have that Li2 of x is defined as a negative integral from 1 to x dt over t. So that would be the logarithm, but now just to have something new, we place here log of 1 minus t in the integrand. So that's the definition of the dilogarithm. Okay. So well, so this is, I mean, if you haven't seen this before, it's just a useful function that appears in Feynman integrals, and it, as I said, it turns out that just with that function and the logarithm and log times log, you can express all these 4-dimensional results at one loop. Okay, now. Yeah, I guess you've also heard from Lance that there's a useful way of thinking about these. So these are examples of iterated integrals, which have some symbols, and so there's something that's common here. So what's really important about the definition of these functions is what the integration kernels are. So here for the logarithm we have dt over t, so that's just a logarithmic integration kernel. And then here we iterate this, so we have this d log t here, and then we have another log. So we could write this as a two-fold integral, and each time we have a logarithmic integration kernel. And so I'm mentioning this because later on we'll generalize this. Now. I'd like to see now how this comes about from differential equations. So just like for the logarithm, it's trivial to differentiate. You see the argument just appears in the integral, so we just get that that's negative 1 over x log of 1 minus x. Now. Just for the purpose of the illustration, I don't like so much the fact that the argument here is at 0. So let me just record this one. So sorry, let me just avoid making a sign mistake here. So let's just like to work with this example. yeah, so if we just, I mean, it's just changing variables. So I just prefer working with this function you see in a minute why that's convenient. But of course, it's just changing the argument. So now, since these functions are all the functions that we need at one loop, it's kind of interesting to see how they could arise in a systematic way. And so now let's do the following. Let's define some quantity f, which will be a vector which involves the three functions. So the most complicated function we have is this Li2 of 1 minus x. And now we see when we differentiate this, what we get is some simple rational function and the logarithm. So if we were thinking about iteratively defining the functions, then we now need a new object, which is this log. So therefore, let me also write the log in this vector. And then finally, if we're now thinking of differentiating this log, we saw that we got the rational function 1 over x, and and just a constant. So let me also record this constant here. Okay, so for now, this is just putting these functions into a vector. But now we can see that something nice happens when we differentiate. So we apply the derivative. We just need to collect factors here. So the first thing that happens is by construction, what we get will be proportional to f again, because all the terms on the right-hand side, the transcendental functions, by construction they're there. And in addition, what we get some rational prefactors. There's 1 over 1 minus x and the 1 over x over here. So I'll write this in a way that seems perhaps a little bit too general, but bear with me for a second. It will become useful. So we have this 1 over x here, and it really just appears in one term in the derivative of a logarithm, but let me write it in this matrix form. So we have a 3 by 3 matrix. There's just one element that's non-zero, and then we have 1 over 1 minus x, and another 3 by 3 matrix, like so. Okay, so this is the system of equations that we get. For later use, I like to call this matrix A and this matrix B, just not to write so much. Good. So that's nice. We see that kind of in this language, we can think of f as the solution to a very simple system of differential equations. So this is a first order linear system of equations. So you know from some lectures presumably that the first order system, it's solved uniquely up to the knowledge of a boundary condition. So here we could also record what the boundary condition is. So there's different choices, but we could just take what is the value of f at x equals 1. So the logarithm, by definition, it vanishes at 1, and the way I've defined this Li2, it actually also vanishes at 0. Actually, I wonder if I made a mistake here. Should this be 1 or 0? Someone in the audience happens to know this off the top of their head? Okay, let's bear that in mind. But for sure, what's true is that Li2 of 0, that's 0. Here you mean, yeah, so probably it's right. The thing I just don't see right now is what happens at x equals 0, how we, so you see here, you're right, there's a potential problem at 0, but actually the logarithm also vanishes, so it's, sorry, I've lost, there you are. So this is actually integrable at t equals 0, but yeah, this is something important to worry about indeed. Yeah, that's a very interesting point. Thanks for asking these questions. So if we just had this, then at t equals 0, that'd be a problem, and but that we avoid anyway, and we also avoid it because the log vanishes. Now you're pointing out another interesting, another important thing is that the log blows up at t equals 1. This is a bit different because in general logarithmic singularities are integrable. However, still there's something to worry about, namely that the logarithm then develops a branch cut, and so this is actually very much like what we had here. That this Li2 function, it has a branch cut starting at x equals 1. So, but the so at the branch point. So here at the branch point, the logarithm, it blows up. That's probably what you're worried about. Now here for the Li2, the situation is very similar. There's a branch point now at x equals 1. However, the function is well defined at x equals 1. One can check it. So in fact, Li2 of 1 is proportional to some, I think it's just pi squared over 6. Yes, Jake? Zero, yeah, so I suspected it. Thank you very much. yeah. Okay, thanks for these comments. So with this definition, it's clear that if the argument is 0, then the function vanishes as it should be. Okay, so we got that figured out. So then if we plug this in, what is this boundary vector? It's just 0, 0, 1. And so now this is a great template for what we'll see later for Feynman integrals, because this differential equation together with this boundary condition completely specifies the functions that we're interested in. Of course, it was a bit artificial, but now you could in a way you could go back and ask yourself, well, if somebody gave me this differential equation, how would I go about solving it? And well, we'll see in a second what's a good way, but it's already clear that there's a unique solution, and the solution is precisely the functions that you need. Now let me do a further manipulation, so to speak, which will turn out to be very useful later. So there's a notion in which these three functions, they are simple, a bit complicated, more complicated. And I think Lance told you about this notion of transcendental weight. So what is this transcendental weight? Transcendental weight. Also, I think colloquially one could say transcendentality, whatever you prefer. So what is this transcendentality? Well, it's essentially the number of integrations you need to obtain your transcendental function. So in the case of a constant, it's 0. So for so here we would say weight. The weight here is 0. For the logarithm, the weight is 1, and for the dilogarithm, the weight is 2. So in that sense, this vector that we have, it's not really nicely balanced. It has, we're mixing objects of different properties, and there's now kind of a formal way of balancing this, which is to introduce some weight counting factor. So let's say that we have a weight counting factor that I call epsilon, which has weight -1. Okay, it's just a definition. And now I'd like to introduce this so that we have a nice vector where the weight is just completely balanced. So let's now define a new vector f. Sorry for using the same notation, but I hope it's not too confusing. And so when we have we have these functions, log of x, Li2 of 1 minus x. So this has weight 0. So now we'd like this also to have weight 0. So we just place some epsilon here, and we place epsilon squared here. Okay. Now it's obviously just a trivial change, so we can go through the motion and see what it does to our differential equation. And it turns out that something very nice happens. We get actually this term back, And now the only modification is that we have epsilon sitting out here in front. So if I now fully specify the equation, this is how it looks like. Thank you. It should. Okay, great. So there's a question. Mm-hmm. Very good. So the dilogarithm has weight 2, and I'd like it to really balance it so that all the elements in this vector have weight 0, that they're comparable. And this is exactly what's happening. Yeah. Now, let's let me write this equation in yet another way, which will also be useful for later. So let's write this in differential form. So equation in differential form. Now here we only have one variable, so it might seem like it's a bit an overkill, but let's say we have this differential, which in our case, there's only one variable x, so it acts as a total derivative and dx, right? So using that notation, I could write the equation as d acting on our function is equal to epsilon. And now I can do a little something here. I can write this as a times differential acting on log x plus, actually, minus b times differential acting on log of 1 minus x times the function f again. Okay, so we've done really nothing. We've just rewritten the equation, but I think it's instructive to count the weight again in this equation. So what do we know? This vector f by construction, it has weight 0. The differential, on the other hand, it removes one integration, so that has weight -1. So on the left-hand side, we have weight -1. And this should equal what we have on the right-hand side. Well, epsilon has weight -1 by definition. This matrix here, the logarithm has weight 1, but the differential has weight -1, so that has weight 0. And then finally, the function f again has weight 0. So this equation makes sense from the point of view of weight, as it should be, of course, as it should do. Okay, but now this epsilon actually turns out to be rather useful when we think about solving the equation. Now let's remember what do we mean by solving? Well, there are some cases. There are some cases maybe where you'd want to solve such an equation as an exact function epsilon, and certainly the case here is one where we could do that because we already know that the dependence on epsilon is really trivial. We've just introduced it. However, we'll see later that this epsilon here, how I introduced it, seemed like a game, but actually later it will actually be related to the epsilon of dimensional regularization. I haven't told you at all yet how this could come about, but this will be what happens later. So later is epsilon comes from dimensional regularization. So for a moment, it's just epsilon, just a formal parameter, but in Feynman diagram calculations, we see this link. So having that in mind, let's now think about how we can solve the equations. Well, so we have our vector f, which depends on x and epsilon, and now we could say, well, we'd like to solve it as some expansion in epsilon. I've normalized things in a way that actually the first term is at 0, right? I mean, this we know already from seeing the solution, but really it doesn't matter here because you see you have f on the left-hand side, on the right-hand side, so you could always multiply by an overall normalization. So I can, up to some overall redefinition of f, I can always assume that it starts at 0. and then we have some coefficient functions fk of x. So this is the way we'd like to think about solving the equation. And now something very nice happens, because we see that on the right-hand side of the equation, there's this factor of epsilon. And this means that when we plug into the equation this ansatz, the series expansion, the equation decouples order by order in epsilon. So let me just abbreviate this. Let's say this is a of x. Then we see that if we plug this in, for example, so let's so we can now look at different powers. So plug this into the differential equation, and then we have, for example, at order epsilon to the 0, we just have a left-hand side which gives a term, so it tells us dx of f0 of x is equal to, and on the right-hand side we have one factor of epsilon, so there's nothing. So this is just 0. So we could solve that equation. And so what's the solution? Well, this tells us that this function, it has to be a constant vector. And what constant vector? Well, we can learn it from our boundary condition that we had earlier. So I haven't said it explicitly, but this is still the same boundary condition. Maybe let me record it here just for completeness. It's also true here. So boundary value f of x equals 1, but for any epsilon is equal to this vector 0, 0, 1. Okay? So that's actually a boundary condition for every order in epsilon. And in particular here, it tells us that this first object is 0, 0, 1. Well, but now we could continue. We could look at the equation at epsilon to the first power, and you'd get dx of f1 of x is something. Now there's a term from the right-hand side, because we have this matrix A of x, which multiplies this vector here, f0 of x, right? But again, it's something simple, because you have a known object on the right-hand side, and this just tells you need to integrate once. And so here we integrate something rational, and then what you find is that f1 of x, well, it's just the function. I mean, I don't go through the algebra now, but I think you can see how. Just want you to see how the pattern works, so you get this weight 1 function that we were looking for. And now we can complete this at the next order. We just have this, and we find that f2 of x is Li2 of 1 minus x, 0, 0. Now, we secretly already know that in this example, this is everything, but we could, of course, verify this. And so if you write out the equation now for the next term, but this is just in this particular example, if you write down what is f3 of x, we would find that by the way this matrix is constructed, when we dot it into this f2, we just find 0, right? And this just means that the higher order terms in this expansion, they're all 0. There's so this f3 is a constant by the boundary condition. Then we know that constant at epsilon cube must be 0, and so on for the higher order terms. Now, this is of course not surprising. It's exactly what we put in, but here we kind of discover it without having to think very much. This is a bit special. So if we have later for Feynman integrals, this is not going to be the case. So so here the epsilon expansion stops stops at epsilon squared. This is very special. It just means that we stopped, the most complicated function we had was with Li2. This is something that's typical when you have four-dimensional finite functions, because then you always have some function which is the most complicated one, and then you have all its derivatives. That's really what we're doing, right? So that's typical for calculations of finite integrals. So in other words, our computation, the most complicated function that our calculation knows is Li2, and then taking two derivatives is enough to specify that function. In contrast, if you have Feynman integrals, so it's different. So it's different for Feynman integrals in general in D equals 4 minus 2 epsilon, because there, as I said earlier, we typically have a Laurent series that in principle can go to any order in epsilon. So you can get functions of any weight. It just goes on and on. So in principle, yeah. So there the expansion doesn't stop. So maybe just to see, I could ask a question for people who know this, or maybe also people who don't know. Why is it really, if you look at this case, and perhaps if you look at these matrices that we computed, is there a way you could see that this expansion stopped? What is it that's really making that happen? Is there? Do you have a guess why that's the case? I heard something. Nilpotent, yes, that's absolutely right. So if you see these matrices here, they are nilpotent matrices. In other words, as you keep multiplying them together, they at some moment they will square to 0, or some power of them will be 0. And that's really secretly, if you think about how this expansion works, that's what makes it stop. And for general Feynman integrals, it'll turn out that we'll have a very similar structure, except that the matrices will be populated with other numbers, more numbers, and then we will not have this nilpotent property. Okay, very good. Now, excellent. So I wanted to connect also to the symbol. Let's see. Yeah, let's connect to that. So let's talk about the connection to the symbol. So just for completeness, let's assume we have this differential equation in the form that we just discussed. So let's say we have a d log x plus b minus b d log 1 minus x times f. So now what is a symbol? Well, I said earlier, the symbol of such a transcendental function really keeps track of the different integration kernels as we iteratively define our functions. And there's a way of formally defining it, which I hope at least one version of it I'm sure you've seen from Lance, but maybe the notation was not exactly the same. So let me just introduce it the way I'd like to talk about it. So let's say g of w is a function of weight w. In the same sense of counting with epsilon that we had earlier. And then, in a way, by definition, what I mean by this is that the differential of this function, it's it's written in the following way. It's a sum of some terms with some coefficients. And I would like it to be a sum of some other functions gi of weight 1 less. So that's kind of what we expect when we differentiate a function, then it should get simpler. Earlier we differentiated the dialog, we got the logarithm. So that's the analog of this. And then there should be some integration kernels, d log, call them d log alpha I. So that's, for me, it's an alternative definition of what I mean by a weight W function. So given this definition, then I say the symbol of G of W so I denote this by S. I heard someone use dollar signs, but yeah, if you want, make a dollar sign out of it. Symbol of G of W is, well, what is it? We can basically read it off from that definition. We take the sum, the coefficient Ci. Well, and these other functions of weight 1 less, they also have symbols. So we're just going to use those. And then we're going to add into the last entry, I'm using this tensor product notation, we're going to add the last entry alpha I. And so that's what tells us iteratively what the symbol of a function is. And now you see the situation is really really great because we have exactly that structure, right? We saw when we solve iteratively for those functions. We have one function of weight of a given weight, and we have to integrate it against the kernel, and that gives us what the next function is. So in other words, here we have, maybe let's remember these equations from up there. So we had d of f w was equal to this. We wrote it in this partial derivative form. We said it's this a of x times f of w minus 1. And so you see, this is exactly the form that we have here. We have the differential of a function. It's given by a sum. The sum here is hidden in the matrix product of low weight functions. So in other words, so if we write this in differential form, so the a in our case was just little a d log x minus b d log 1 minus x, and there we have the f w minus 1. So you see, you can iteratively define the symbol. Once you have the f w minus 1, you just have each step you have two terms. One where you add on to the symbol the letter x, and one where you add on the letter 1 minus x. And so Jake would tell you that you can write a one-line Mathematica code that just implements this. And so you just keep going. You know, you have the your weight 1 symbol. From that you get the weight 2 symbol, weight 3, and so on. And so in other words, you can from the differential equations you can immediately read off the symbol of the functions to any weight that you like. So symbol can be read off from the differential equations to any desired weight. I don't know, maybe this was just a tiny bit abstract, so we could well, we could just make a quick example. Let's say we start with the weight 1, because that's really where it starts being interesting. Yeah. So really what we have, so we have a logarithm. So the symbol of the logarithm. That's always a bit of a notational problem for me because it's just usually we just write the argument x, and then you kind of need to know that it's a symbol. So I could write it like this. I sometimes also like to use this bracket notation just to see that it's something different from the polynomial x. But anyway, so in other words. Some people like to use this notation with tensor that I've also used, and then in some other papers you'll find equivalently some bracket notation. So I just want to mention it, whichever way is less confusing to you. And so now, if we apply this definition to the dilogarithm, let's see. Actually, it's probably easiest if we refer to the equation up there, which is exactly what we get if we expand out the matrix. So then we see that 1 over 1 minus x times log x. So here we just have one term. Now let's write it in a useful way. So this prefactor, we can say it's negative dx of log 1 minus x. Times log x, and let's now compare. So we have a log x here. We have the d log 1 minus x, and in our definition, of course, I've written the terms the other way around. So we have this term here, and that is our lower weight function. So then according to the definition, we'd say the symbol of Li2 of 1 minus x is equal to, we have this constant c is now -1, so I put it out there. Then we need the symbol of log x, so that's x. And then we add on in the last spot now the symbol of this, which is 1 minus x. Yeah, I don't know. You've probably done quite a bit with symbols with Lance, that actually even much more sophisticated things. But I just like to point out that they're also really nice for some even for understanding these functions better. But I just like to mention this in passing. So you can use symbols to discover function identities. So let me just mention this quickly here because it kind of fits into this discussion. So it turns out, and this is really, of course, some old stuff, so that the dilogarithm, it satisfies identities that if you have Li2 of x, it's actually related to this Li2 of 1 minus x that we've been discussing through some functional identity. And so let me just write it for you. So this is the identity. This is equal to 0. Now, you might wonder, okay, why do we care about such identities? Maybe it's some curiosity. I mean, the main thing is that we got our answer and it's analytic, so what more to ask for? Well, one issue is that if you do a calculation and you get Li2 of x, and your friend does another calculation and they have a different form of writing it, maybe you'd like to know if it's the same. And so that alone is kind of a good reason for understanding these identities. Maybe also another reason is that this really represents an ambiguity. It could be a 0 in, let's say you have a long page of calculations, and if you have a hidden 0 like this, it could multiply anything, in particular something very complicated. And that's usually not a good situation to be in, because then you don't know if you've really exhausted all the possible simplifications. And so you, like in Jake's talk, there might have been some huge simplification that led to this one-line expression, but maybe one is not seeing it because of something like this. And so one very neat feature of a symbol method is that it makes identities like this one manifest. In other words, so you could think about how to prove this identity, and I'm sure you'd find some ways of doing so. But if you just wanted to get a hint for whether or not it's true, what you can do is you can take each of these terms and translate them and ask, what is its symbol? And so the statement is that if you compute the symbol of this thing, then, I mean, since the identity holds, that also the symbol must be 0. However, the difference now is that at symbol level, you can see this in elementary ways, and in particular using just some algebra. So only algebra needed to see this. And so that's of course a great situation to be in. Now I won't be doing this calculation here, but I think if you haven't seen it, I mean that's really a great exercise. I mean I don't want to give you exercises for these lectures because I know we have a very full schedule. But at some moment, if you have some time, that's really a nice thing to see, and then gives you kind of a hands-on feeling how to work with those symbols. Now. I don't want to cut into the coffee break, so let me just wrap up very soon. Go, please do. Yes, absolutely, that can happen. However, it happens in a way that's useful. If it does happen, it happens in a way that's useful. So in the sense you can quantify to what extent, what's missing. People call this beyond the symbol. And I should say there's also some sophistications that, I don't know if you've heard from Lance about the co-product, which kind of also deals with that a bit more systematically. But I think there's a very simple statement I can make. And maybe it's another angle on these differential equations. We had these first-order differential equations, the system of equation, which fully define the answer up to an integration constant. So from the viewpoint of a system, it was one integration constant, one vector. However, we could view it from the point of view of the logarithm function, because we have here also a weight 2 function. And if we view it this way, then there were actually 3 integration constants that we needed, because the vector consisted of 3 elements. So if we view the system as the definition of a dilogarithm, there's 3 integration constants, one at weight 0, one at weight 1, and one at weight 2. And it's exactly the 2 of those integration constants that we'd be potentially missing in this example. So one way of saying it is that the symbol checks identities up to integration constants. I use a plural because you might say, well, here's a constant, right? And that's one of these constants. Another constant might be something like I pi times log x, which we would, for the moment, we'd throw away because it's something which can appear as a integration constant in this intermediate step. So what does it mean? It means that if you have a symbol identity, you're guaranteed for this to hold, and you could quantify, if you want, one useful way is to think about these equations and how you iteratively integrate them up in order to make sure that you're not missing anything. Are there other questions? If you're asking me as a physicist, yes. I don't know if yes, but that's correct. It's in the framework that I've been discussing. It really boils down to something very simple. So that we have log of a product, that this at symbol level it's always log of the sum of the 2 logs. So the way it works that you kind of differentiate down until you get to the logarithms. Then you can use these simple identities at the level of integration kernels. And then you put things together again. So it really boils down to this identity. It's rather trivial. If we had more complicated functions, maybe elliptic polylogarithms and so on, then I honestly don't know. But in the context of these multiple polylogarithms, it's always identity at a fixed weight. Yes?
Can you always guarantee that, say, at epsilon to the 0, that f will be, the derivative will be 0, and then you can start the iteration, or?
Right. So you're referring to the way we iteratively solve the equations.
Yeah.
So here I said that the expansion started at epsilon to the 0.
Yeah.
In general, that's not the case. So there's two ways. In principle, normally when you have some particular Feynman diagrams that you look at, you might know through some analysis of their divergence structure, some power counting, for example, you might know what the leading pole is, and then you can anticipate it. However, in a way, it does not really matter for the reason that the equations are homogeneous. So we have f on the left and on the right-hand side. So the starting point really doesn't matter. It ultimately. It doesn't matter in this expansion. It really, where you learn about it, it comes in through the boundary condition. So the boundary condition really tells you what is the exact order where you need to start.
So there's always a starting point, but it might not necessarily be at 0. Is that what you're saying?
That's correct, yes. That's correct.
Thanks.
Yeah.
Okay.
Maybe just, let me just say one more thing, and then if maybe there's a further question. So to wrap up this morning lecture, we've taken a bit of an abstract approach. I told you logarithms, dilogarithms are useful, and let's think about them from how they come out of some differential equations. The reason I like this is that it seems like this is a very useful framework that if you needed to define those functions, one good way are those equations. And now, on the other hand, if we think that Feynman integrals evaluate to those functions, the question is, can we understand how that happens? And ideally, can we map the differential equations that we get for Feynman integrals? Can we map to those equations that literally are the definitions of the functions? So if that scenario comes true, then it's great, because then we could just read off what the answer is, very much in the same way that we've done here. And maybe I'd just like to end by saying that this is actually the case, and we understand how that works. There's some Feynman integrals where literally you get this very simple system with the two poles that we just looked at. There's other Feynman diagrams where then you get a similar structure, but you get more terms on the right-hand side. And so one example of that is these hexagon functions that Lance showed you, where as opposed to two terms on the right-hand side, 1 over x, 1 over 1 minus x, you get several of them, I believe nine terms. And then you have iterated integrals that are defined in such a space. And that question that really depends on the kinematics and the structure of the Feynman diagram. But what remains true is that we can use this framework to think about how the functions, how the Feynman integrals evaluate to the functions. So I don't want to go over time, so I'll stop there, and we'll connect with that then in the afternoon and see concretely how we go from Feynman integrals to these systems of equations.
Okay, thank you, Johannes. If there are any more urgent questions. If not, let's go for a break. Let's thank again.
We have 20 minutes, I guess.
Oni si účtujou extra práci a pak ještě těch 12%.
A ta extra práce ani nepotřebujou.